Hello, welcome back. This is the second video on reaction rates. I have a guest lecturer who's come in, although she doesn't seem very interested in talking very much. Um, what we've got first, so this lecture is going to be, this is going to be on reaction rates again. We're going to look at concentration and rate laws. We're going to define what a rate law is, and it's basically an easier way of talking about concentration, so we don't have to graph every instant of, I got cat hair all over me. Um, so I apologize for the cloud of fur that's currently enveloping me. Um, we're not going to, oh my gosh, we're talking about rate laws, and rate laws are a nice way to kind of consolidate a reaction rate into one number as opposed to this kind of ever-changing number that we saw with the graph of the disappearing concentration and all that other kind of stuff, right? So rate laws are nice because they're simpler than the instantaneous rates that we talked about in the previous slides, and they're easier to take it's going to be easier to take one reaction and compare it to another because we're going to kind of set some rules on what the rate law means and when we can use it and all of that other good stuff. So we're going to standardize all of this and give us one number as opposed to an ever-changing number that's hard to pin down. Okay, so that's the goal at least. We'll see how it goes. All right. So to do this, we talk about the instantaneous rate. So instead of talking about the kind of always changing rate, I don't have my pen. Give me 1 minute. I have my pen. All right, so instead of talking about the ever-changing rate, so um, instead of the instantaneous rate, right, which is the rate at however many seconds, right, the rate at 300 seconds at a particular time, we consider the initial rate. Right, and the initial rate is just rate at time equals 0. So it's the rate that we start at, right, which makes good sense because that way we can just say, okay, the reaction rate will slow down as concentration goes down, but this is our initial reaction rate for this reaction. So let's talk about a particular reaction because I think this is always easier when we look at examples. I'm going to take NH4 plus NO2 minus, and that's going to go to N2 gas plus 2 molecules of H2O. I was looking at the wrong equation there for a second. Okay. So again, we have starting materials, NH4 plus and NO2 minus. We have products, N2 gas and H2O. And what we're going to look at is what happens. So in order to figure out the initial rate at time 0, right, we can't really measure what the concentration is at time 0 because there's going to be no change from our initial because that is the initial time. And so what we look at is what happens to the initial rate if we change the concentration of NH4 plus. Right, so remember the square brackets mean concentration of whatever is inside them. So if we change the concentration of NH4 plus, so let's say that we do this, right, and we say we run the first one, if we double, well, we run the first one, right, with concentration NH4 plus equals 1 molar, we get a rate, we get an initial rate, I should say. I'd always just say rate because that's all we talk about. But rate here is the initial rate. We get a rate of whatever, let's say 0.02 molarity per second. Right? We run it again, NH4 plus, but this time we we double the concentration, 2.0 molar, and our rate now equals 0.04 molarity per second. Right? And so we think we kind of see the pattern, but guess we might as well triple check it, right? More runs is better. And we run this again, let's say we run it at 3 molar this time, And so our rate in this one comes out to be approximately 0.06 molarity per second. Right? And so you can kind of see what's happening, right? Every time we change the concentration of NH4 plus, the rate changes by exactly the same amount. If we double the concentration, the rate doubles. If we triple the concentration, the rate triples, etc. And so we can say that the rate equals some number, right? I'm going to just use K for that, times the concentration of NH4 plus. But we have another starting material. What happens if we do it with the other one, right? So NO2 minus, well, let's say this time we start with 0.5 molar, right? And our rate is equal to, I don't know, 0.03 molarity per second. We double it. And we see that the rate doubles there as well. Now, whenever I'm doing this, so in these two cases, right, we're keeping the concentration of NH4 plus constant. Right, so let's say that in both of these cases, we keep NH4 plus at 1 molar, right? Or maybe it's at 3 molar, right? If NH4 plus is at 3 molar and this one's at 1 molar, we always get 0.06. And so in this case, constant at 3.0 molar, right? That's fine. In this one, the concentration of NO2 minus is constant, or in these three examples, the concentration of NO2 minus is constant at 1 molar. Right? And so when we have 3 molar of NH4 plus and 1 molar of NO2 minus, 0.06 molar per second. 3 molar NH4 plus, 1 molar NO2 minus, 0.06 moles per second. Right? And so we can also say that the rate is equal to K times the concentration of NO2 minus. Now, because K is a constant in both cases, right, we can just combine these two. We just take K times other K, and that'll just give us another constant, right? A constant times a constant is just a third constant. And so since we don't know what the value of K is, we can just say, well, we're multiplying these two things together. And this expression still works, right? This right here is our rate law. Oops. That's a W. That's a terrible W. I'm going to try again. Rate law, right? And so what this does is this accounts for all of our evidence. If we increase the amount of NH4 plus, then we see the rate increase in a linear fashion, right? Double it, the rate gets doubled. Triple it, the rate gets tripled. If we increase the concentration of NO2 minus, the same thing happens. And that's what this rate law shows, right? If we double the concentration of NH4 plus, that means we basically have K times 2 times the concentration of NH4 plus times the concentration of NO minus. That 2 means that the rate will overall be doubled. If we double the concentration of NO2 minus, the rate is also doubled. If we double both of them, right, so we could predict now, if we start with 6 molar NH4 plus and 2 molar NO2 minus, right, we can predict what that will look like. So 6 molar NH4 plus and 2 molar NO2 minus, right, that means that we're going to double the rate because the NH4 plus is doubled, and then we're going to double the rate again because the NO2 minus is doubled. And so in that case, the rate would equal 0.24 molarity per second, right? This is 2 times 2 times 0.06. That gives us that number, right? Because we doubled both, doubling and doubling, we have to multiply by 2 twice. And so we get 0.24 molarity per second. So this rate law, once we figure out the rate law, now we don't need to run the experiment. We can just take each one of these, and we can take any concentration of NH4 plus, any concentration of NO2 minus, and just by